ladies and gentlemen. It is my greatest pleasure to welcome you all on behalf of the organizing of these outstanding events. It is also a great honor and privilege to welcome Professor Bernard Lucas Feringa, an eminent organic chemist working on the field of molecular nanotechnology. He was the first to develop molecular motors and was awarded the Nobel Prize in Chemistry in 2016, together with Jean-Pierre Sauvage and Sir Fraser Stoddart, for the design and synthesis of molecular machines. My name is András Perczel, and please allow me to introduce our distinguished guests just very briefly. Professor Ben Feringa graduated from the University of Groningen, the Netherlands, and received his PhD in 1978. He first did research at the Royal Dutch Shell Laboratory in Amsterdam, where he worked on organic chemistry, synthesis, oxidation, and photochemistry. From 84 to 88, he was a lecturer, and then since 88, he has been appointed professor and chair of organic chemistry at the University of Groningen. Since 2003, he has been the Jacob H. van 't Hoff Distinguished Professor of Molecular Sciences. Now, he has many and several academic and professional responsibilities and roles in scientific societies, but rather than list them all, allow me to refer to just one of his ideas and one of his quotes. During his Nobel lecture, Professor Feringa said that if you want to design an airplane, you don't work on improving the way how birds fly. Similarly, to discover the light bulb, which you use for electricity to produce light, you don't go on and perfect wax candles. The question you ask in basic science is of paramount importance. He asks fundamental questions such as, how do you control rotational motion? How do you make molecular fragments rotating clockwise or counterclockwise? Not only did they find fascinating answers, but they constructed rotating molecular vehicles that managed to build the first four-wheel vehicle, and which consumes light only. One of his favorite quotes is, "The best way to predict the future is to invent it." I think which is just wonderful and outstanding. So with that, I'm very pleased to announce the title and of the presentation of his talk today, The Art of Building Small from Molecular Switches to Motors. Professor Feringa.
Thank you very much. Okay, thank you very much for these very kind words and the introduction. And it's a great honor and a great pleasure to be here and to share with you some of my journey. What I want to do today is, I don't want to go too much into all the details, of the chemistry, but more about, why we discovered this, what we did discover, and what kind of applications we are looking forward, etc. And once again, it was great, to meet here all the people, the students, I discussed with today. It's wonderful to be here. Okay, this is fine, thank you. So I want to start my journey with the question that I often get: why do we need molecular machines? Why do we need molecular motors? And this was a bit the question, that these Wright brothers got more than 100 years ago. People were asking, why does mankind need to fly? If God wanted us to fly, he would have given us wings. Nobody, of course, would have predicted that 100 years after the Wright brothers, we would build the Boeing 747 or the Airbus in Europe that can carry 400 people across the ocean, 1,000 kilometers an hour, 10,000 miles. We admire the flying pigeon, but try to carry 400 people 1,000 kilometers an hour across the ocean with a pigeon, you will fail. Yes, we admire the flying pigeon, but this is a fantastic highlight of human mankind, of engineering. where chemistry, physics, material science, all this engineering come together, computer science, to build an aircraft like this. But we should also be very modest, because 100 years after the Wright brothers, we cannot build a pigeon. And my friends in biology tell me we cannot build a single cell of the pigeon. We cannot build even one of the machineries of the cell of the pigeon. So we should be a bit modest, you know. So I suppose everybody has a smartphone. I asked it earlier today, you know, and there was one person who had not a smartphone. How many people have no smartphone here? Again, the same person probably, yes. So this is a very precious person, you know, very precious species. So we realize this is fundamental science, yeah, to go to method society. Which fundamental scientific questions, novel insights and discoveries were made? And we should not forget that it was a 50-year journey, because it was in the late 40s, early 50s of the past century that the physics make the first transistors, you know, and that the chemists worked on the liquid crystal materials. And nobody would know that we would have a smartphone. The word did not exist. IBM was just building the first computer, I think, that would fill this room and could do way less than your smartphone. And it was, of course, John Goodenow and his colleagues, you know, in the early 80s that invented the lithium battery. Otherwise, we would not have electric cars and we would not power our smartphones. So it was a 50-year journey to change the world. And it was physics, chemistry, yeah, engineering, computer scientists, and many others that came together to make this possible. And indeed, it changed the world. We cannot deny that. So, the path to the future, science and discovery, like we do at this university, is in this beautiful garden of science, we ask questions. That's the most important. Don't forget that. Asking questions. It's an adventure in the unknown, but also serendipity plays an important role. Often we make accidental discoveries, and sometimes that completely changes our picture and makes really progress. So in the joy of discovery, we see lots of challenges. Challenges for our peoples. Dreams, yeah, for our students. Opportunities for our society and industry. It's indeed an adventure in the unknown. But often we get lost, and then we see these question marks here in this garden of knowledge and science, which we have never thought about. And these are often the most beautiful questions, and we get the most fantastic results. So we have to go far beyond our horizon, looking at all the problems that we face today, yeah, with respect to sustainability, new technologies, and I will talk a little bit about nanotechnology. This was my horizon when I was a small boy. And you know, I lived in a farm on the German border in the northeastern part of the country, and there was a lot of wilderness, and it was fantastic to discover, you know, and to go into that kind of adventure, asking questions to my parents. And I was reading books already as a child about adventurers and about discoveries. And I was asking my parents, you know, why is this tiny seed giving this, yeah, beautiful flower? Yeah? Why is the sky blue, and why is this orange or red? And these potatoes are white. Yeah? And so I grew up in a family of 10. This is me, you know, when I just left elementary school, I think. And I got a lot of inspiration by my parents, asking them questions, you know, reading books. But the most important thing probably was when I went to high school, to gymnasium, and I had a teacher, Gerard Op de Weeg, who was my chemistry and physics teacher, and he was such an inspiring person because he did experiments with us, and he was encouraging us, and I got acquainted with chemistry, physics, mathematics, etc., and I wanted to study chemistry. And then I went to the university. This was my professor, Hans Winberg, an American professor, and he challenged us a lot. This is the University of Groningen, by the way, and he challenged us a lot, and I remember he gave me a topic that was impossible. My colleagues in the lab, the students said, this is impossible. But Winberg, my professor, said, we will make the Americans jealous. This was my first molecule that I ever made. And I came to his office and he said, Ben, nobody has ever made this molecule in the world. It was a totally useless molecule, but it was my first molecule that I made. And I was so proud, you know. I was so proud that I wanted to continue to be a chemist. So this is what I saw recently at the Clinton High School. Look, when you educate one person, you can change a life. When you educate many, you can change the world. That's what we're doing, eh? So let me give credit to our teachers. Teachers opens windows and shape the future with our young talents. And we should value our teachers at all levels, you know, from elementary schools to the universities, because they will change the world. So after my PhD, I worked for Shell for 6.5 years in the Shell Central Research Laboratories in Amsterdam, mainly in catalysis, and then in the Shell Bioscience Center in the UK. But I decided to go back to the university because I wanted to build up my own research team. And since then, I have been working on molecules. In the art of building small, I developed this passion for molecules, designing my own molecular world. And together with our students, we do chemical synthesis, designing molecules and materials in the lab. You all know that. And because there are many chemists here, and we sometimes design that simply because we make more beautiful molecules. Now then you ask me, what is a beautiful molecule? I cannot tell you, because it's very personal. It's like a beautiful piece of music or a picture or so, or a painting. But I want to emphasize, you all know, when you are in a laboratory, like in this building here, building molecules and materials, we share a universal language. Last week I was in China. I was lecturing at universities, and I was also in high schools, and I don't speak Chinese. But these Chinese students, when they know the periodic table, or they know this is the structure of a sugar, we share a universal language. That's the same in mathematics, of course, in physics, but also in chemistry. And this is something that connects us together. We have no borders. There's a lot of talk about borders these days. But scientists, we go beyond borders. That's our duty. We have international cooperation, and we share a passion for discovery. So, I want to use this quote here of Pasteur, yeah? Discovering our future. Science knows no country, because knowledge belongs to humanity and is the torch which illuminates the world. And we should always, at our universities, keep this in mind. I think it's really crucial. So, having the periodic table, it's amazing, eh? With this handful of elements, this is everything here. Everything you see here, including everything in your own body, everything in outer space, is built up of these elements. All the material that we can touch, we can feel, we can see. It's pretty amazing what you can do with all these elements and with these molecules, etc. And so this was Mendeleev, which we should put in the same category as Newton and Einstein, I think, because he gave us the periodic table. But then I'll show you here, this is the formula of the human body. Yeah? I don't know if you realize, hydrogen 375 million, oxygen, carbon 85 million, nitrogen, oxygen 132 million, carbon 85 million, and one lonely cobalt. There's also a cobalting body. Professor, can you stand up for a moment and look at the audience? Look, 60% water. That's why there is so much hydrogen and oxygen, and a few handful of other molecules. But he looks pretty okay, no? Fantastic man. So, can you imagine that this is the formula of your body? Now the question to the students. Are there more distinct elements in your body or in your smartphone? You don't have to give an answer because you don't know. You have no smartphone. But the students, is there more or less? Okay, I'll tell you. This is your smartphone. In a smartphone, there are more distinct elements than in your body. I don't know if you realize that. Your body is pretty complex. Eh? It's the most complex thing I know on this earth. But in a smartphone, when you simply look at the elements, your smartphone is more complex than a human body. Okay, it's a joke. But this is true. This is reality. And we all know the problems with some of these elements we have to recycle, because they are the precious elements in all our electronic components and so, and they might be scarce. So, chemists, you know, are really good in building molecules, we all know that. 2 carbons, 4 hydrogens, ethylene, plastic, 160 million tons a year. Very simple. Or vitamin B12, carbon, hydrogen, oxygen, etc. A very complex molecule, for the first time synthesized by Woodward and Eschenmoser. Only, it was called the Mount Everest of synthetic chemistry in those days. 35 tons a year. Why is that? That's the whole world prediction. Because you need only microgram quantities to stay healthy. Complex, simple. Small volumes, huge volumes. So this is what chemistry does. Not in isolation, of course, together with our material science, our engineers, yeah, physics, biologists, but we make the drugs and the dyes, cables, cars, yeah, clothes, all the components of your smartphone, all the plastics, etc. Ladies and gentlemen, be proud to be a chemist. This is what makes modern society. Yeah? Despite some of the arguments you hear, we have a few things to solve in the future, but be proud to be a chemist. But you also realize immediately, despite the fact that we can all do all these things, there is nothing that moves controlled. So, in your body, there is motion. Look, there are the rotary motors. Yeah? There are these motors that transport things in your cells. There is this ribosome, this fantastic robot that makes most of the proteins. Look at this bacteria flagella motor that makes the bacteria swim in your guts, going forward and backward. And the optical switching, the process of information retrieval, yeah, processing in your eye. This is where we started our journey, you know, in this field of nanotechnology. But so we thought, can we make things that have controlled movement, like in Mother Nature? And this is what I've been focusing on most of my career. Now, just to bring everybody on par, you all know this, but 1 nanometer is 1 billion of a meter. You know, this is one of my hairs, huh? You see? No, you can see? This is one of my hairs. Yeah, I don't take a second one, you know. I want to. But you know, the cross-section of a human hair is 80,000 nanometer. Have you ever thought about that? Size matters, yes, it makes a big difference, you know. And so, we have developed all these new techniques, of course, not me, but our communities, where we can read and see atoms and molecules. You cannot use a microscope, but with this STM and AFM, etc., you can feel and see atoms. This is Nano USA written, yeah, by IBM. And on the cross-section of this hair, yeah, you can write 250 million letters. So part of your library can be written on the cross-section of a human hair. This is the world of nanotechnology. And of course there are nano products. You see nanoparticles in the sunscreen. They are really good. They are so nice, you know. They are also a bit expensive, but these are small particles. And look at these quantum dots, yeah? If you want to see on a beautiful TV screen, use these screens that have these quantum dots, you know, because they have beautiful luminescence. So LCD screens. But this is all hard materials. And what we are working on is, of course, in the world of the soft materials. So, this terminology, nanotechnology, was introduced by Richard Feynman in 1959. And he said there's plenty of room at the bottom. What he meant is, go to the level of the molecules and atoms and build like Mother Nature does it. Because this is typically what has happened there. The first computer going down and down and down, and we are now at the nano level with our chips technology. But that is top down. But go bottom up. Yeah? And it took 50 years, and then we got this magic all together with Jean-Pierre Sauvage and Fraser Stoddart to build the first primitive machine-type structures. And so, to realize this is an artificial robot in a car manufacturing plant. This is the robot in your body that I mentioned before. Look, this is hard material, this is soft material. But there is a factor of length scale. 2 meters, 20 nanometers. 1 billion times smaller. That's the nano world. Hard versus soft, that's in your body. And of course, somebody asked me earlier today, it's about this motion. It's not so much about getting motion. There's Brownian motion everywhere. In molecules. The Brownian stars, molecules move like crazy. Unless you have them on a surface or in a condensed matrix. So it's the world of the low Reynolds numbers, and you have to fight the Brownian motion. So it's much more about controlling motion. So let me start with switches. Yeah? We all know what a switch is. Switching your laptop on, switching your smartphone on, the light on, your car. So this is the most beautiful switch. This is the retinol in the eye. I'm sure you all learned this in school. It has a band structure. This is a linear structure. You switch back and forth. Because if it switches only once, I would see this lady only once, and then it would be over. But it has to switch back and forth. Otherwise, you know, you cannot retrieve the information to your brain, and you cannot do this process of phishing. But you cannot use this to build a computer. So we thought, many years ago now, can we build artificial switches and store information at the molecular level. 0, 1, 0, 1 in an artificial system. So a binary system at the molecular level. And you see here, we have this still beam type structures. We can switch with 2 wavelengths of light, back and forth. And you might ask, why do these guys make these molecules chiral? So this is an M, a minus helix, and this is a plus, a positive helix. And the reason was, when we were working on these kind of materials, these photochromic materials as they are called, we realized that when you retrieve the information with light, we want to make all optical data storage systems and optical computing. But when you retrieve the information with light, you often switch back. So you lose part of your information. So we make them chiral, like left-handed and right-handed forms. And then we could detect the information very easily without destroying. And then we make devices, you see here, gold, this is gold islands, these are devices with molecules, and we can write zeros and ones. And so, I can ask this question, I know the senior people still know that, the junior people might not know what a compact disc is, yeah? But a compact disc was modern technology when I was a student. Now it's a bit old-fashioned technology, with all the smartphones. But you know, we wrote zeros and ones in plastic, zeros and ones, and the storage capacity of one CD is this megabytes. So you can play 240 years music with one compact disc. Your grandparents and grandchildren for 6 generations, one compact disc, you can continuously play music for 240 years. This is the potential of nanotechnology. This is not reality, because we can write zeros and ones. We did that in the laboratory, no problem. But then one molecule is here and one molecule outside the campus somewhere there, you know. And then you have to separate, because otherwise you get interference and so. We have not solved that problem. But what we do is, we build these switches, and we have a big program in the last 10 years. We build the switches in drugs to make smart pharmaceuticals. This field is called photopharmacology. So the idea is, when you go to a doctor, you want to have a drug that does something, that's active. And we want to have something that is not active, but that we can activate on the spot with a flash of light. On, off. High precision in therapeutic action. And there are several groups around the world working on this now. So, after the COVID, you might think, you know, that there are not other problems. Now, I tell you, the World Health Organization said bacterial resistance is one of humanity's ticking time bombs. And of course, we all know all the problems with cancer treatment and chemotherapy, all the nasty side effects. So, we focused on these two, making switchable antibiotics and making smart chemotherapy. And so here is an example. This is Cipro. I'm sure when you go to the clinic here, you get a broad spectrum antibiotic, you will get Cipro. We put in a light switch. This is an azobenzene. You see this is a linear molecule and this is a band molecule. And we switch with light. It activates with light and it deactivates automatically. And it can deactivate automatically after 2 hours, after 24 hours, depending how we engineer the molecules. This is typically what synthetic chemists do, of course. You can change the barriers for isomerization, etc. And you see, the idea is you have an infection here. The antibiotic is not active. It doesn't do anything with your normal bacteria. You irradiate here on the spot. You activate it for a couple of hours. It does its job, and then it's deactivated. No resistance build-up. And we work on the control of biofilm formation, which is a serious issue in the hospital. But this is what my students do. You see, this is a Petri disk. Here the bacteria grow normal. Here they cover it. Here they cover it. Here they irradiate with light. And they grow a yin-yang figure of bacteria, just controlling the antibiotic activity with light. We also go to anti-cancer, chemotherapy. We switch this proteasome inhibitor, and we can switch on and off and try to avoid nasty side effects. Once again, this is early days. We are not at the stage yet that we are in the clinic, although some people get into this stage where they can do experiments in the clinic. We are in tissues and so, but in cell cultures it all works fine. But there is one issue you might ask. What is the key issue? The key issue, of course, is what light to use. Because you cannot use, in the beginning we used ultraviolet light, blue light, but that is dangerous. And you know, when you go to the beach in the summer, you use sunscreen. But we have to look red light, because red light is not dangerous, and just a red laser can go straight through your finger. So this is what is at stake. You have to be in this part of the spectrum. And typically this is again what gammas do. They modify molecules, and you see you can walk through the whole spectrum towards the red. And now we have switches that are in the infrared region. And many groups in the world have in the last couple of years worked on this. So we have now an antibiotic, you see. Here is the original one, here's the one. We can switch now with 650 nanometer or so. So now we can use it in cells, in tissues, and hopefully in the near future also in humans, you know, once we get the approval, you know, for these kind of things. So this is where we stand, yeah? And yeah, this is the beauty of science. We should not forget, sometimes as a scientist you feel a bit like an artist, like a musician or a painter or whatever. And science is also beautiful. And this, there was a photographer, a science photographer that came to our labs because they were in Cambridge and in Harvard and in many places because they want to make an exhibition of science pictures. And they took here a picture of the fingers of this is the hand of my PhD student that did for the first time the red switchable antibiotic. So that was in several musea, exhibitions. So as a PhD student, you can do a major discovery in the lab and get a nice paper, but you can also end up in an arts exhibition, you know. So I was very proud of this student. So when we talk about a cell, before I go to the motor, we all know cells have cell membranes, yeah? And I think it was mentioned earlier, in the cell membrane, you have these channel proteins, you know. I know many people here work on proteins. This is the top view. You see it's closed and it's open. This is a mechanosensitive channel from the coli bacteria. So in your guts, in the coli bacteria, you have this channel protein that can open and close to protect the protein from osmotic pressure, explosion, these things. So things flow out of the cell. And we thought, oh wow, this is cool. Sometimes it pays off, you know, to talk with some colleague, you know, in another discipline. Because when we realized that in biology there were these beautiful channel proteins and they open a 3 to 4 nanometer channel, we thought, wouldn't it be cool to build a light switch in the channel and open and close it? And it worked like a charm. You see here, we did genetic modification, we built in light switches, we reconstituted in a giant vesicle or an artificial cell. You can load it up with a drug or a dye, irradiate with light, it opens, things go on. Controlled drug delivery. Taking advantage of Mother Nature and engineering with synthetic, in this case a light switch, to make it possible that we can control, open and pour at the nanoscale. And this is our most recent result, yeah, that we took now a protein from a spider, frag protein. Insects, some insects, be careful, because they have these very toxic proteins. And this protein, they can assemble to form a pore in a cell membrane. And what we did is, we put again a switch, and when we switch this with light, suddenly they start to assemble and form a pore in the cell membrane. So, using this system, we drill a hole in a cancer cell. So we have killed cancer cells by drilling a hole in the cancer cell just by irradiating with light. So maybe in the future this will be molecular surgery. Yeah? Look at, a couple of years ahead. So, in the future, the bio-nano future, where I emphasized during the first part of my talk, crossing the borders of chemistry, physics, biology, and medicine, smart medicines, yeah, rewiring the brain, optogenetics. A lot of people in neuroscience work on this. Genomics, DNA nanotechnology. We all know about CRISPR-Cas and so, which will be very important. But also networks complexity. This is not the metro of Paris. This is just a small part of biological pathways. And if we can modulate, block certain pathways, we learn a lot more about the biological process. So this is our goals. Okay, but let me go to motors, because you are waiting, when is this guy coming with his motors? So these were all switches, yeah? But you know, a molecular motor pushes a thing out of equilibrium. We all know when something moves, and this is dead and this is moving. I sometimes see on television in a program, be in equilibrium. I read it in magazines, be in equilibrium with yourself. Ladies and gentlemen, these machines in your body push the system constantly out of equilibrium. There are millions and billions of these motors that push the body, the living system, out of equilibrium. If you are in equilibrium, you are dead. A biological system is out of equilibrium thanks to these nanomachines. So, you have to be in balance or in harmony, and that's fine. Be in harmony with your life or in balance, that's fine. But don't be in equilibrium. So this is the most beautiful. Who heard about Max Verstappen? The guy who wins all the Formula 1 races these days, you know? Yeah? We are very proud of this guy. He's Dutch, you know? So, he has a beautiful motor in his car, but this is by far the most fantastic motor that you can think of. This is the ATPase rotary motor in your cell membranes that acts as a pump and makes the fuel in your body, the ATP. It rotates, yeah? Nanomate, it rotates, you see? It's a nano-sized motor, and there are billions of them in your body. You know how much ATP it produces? Half your body weight. So if you are 80 kilograms, it produces 40 kilograms every 24 hours. Now, I like the food here, don't worry, but I don't eat 40 kilograms or 30 kilograms every day. This is all recycled, you know. This is what nature does. It recycles most of these components, of course. Half your body weight is recycled by these tiny machines every 24 hours. Can you imagine? Did you ever thought about it? What is one of the most pressing challenges that we are facing in science, in material science, in chemistry, you know, in engineering, is how to recycle our materials in the future. Come on, guys, plastic recycling. We are not smart enough. Your body recycles half your body weight every 24 hours. We have to learn how to do this. Yes? So, what is the key problem, the scientific problem? To build a rotary motor, because we want to make something that rotates. Of course, you have to control rotary motion, so you have to put in energy. Otherwise, it will not move. If there's no fuel in your car or no electricity in your electric car, it will not move. But also, if there's equal probability going backward and forward, you wouldn't get anywhere. It has to go either forward or backward. So we have to break the symmetry, how to control left and right. And we do that by using chirality. And yeah, here is the DNA, we all know this, the right-handed helix, and it was called the Mona Lisa of modern science by Nature several years ago, and I think we all agree on that. So we build these motors, either like our switches, either left-handed or right-handed. And then we can control, and here is the tiniest motor in the world. Yeah, it's powered by light. It's unidirectional rotation, so we can rotate clockwise or we can rotate counterclockwise. The size is 1 nanometer, and it's due to the chirality of the motor we built. Now, you might ask, hey, how is it possible, you know? This is a double bond. How can you rotate around a double bond? But of course, you excite with light, like in your eye, the retinol, you excite, you break temporarily the double bond, it spins. That is how it works. So here it is. Powered by light, 4 steps, and it rotates either clockwise or counterclockwise, depending on if we make it left-handed or right-handed. So it's 4 steps: photochemical double bond isomerization, helix inversion, double bond isomerization, helix inversion. So in fact, what you do is, with the energy of the light, you power it to make a high-energy system. It flips the helix, it continues in the same direction. Yeah? This is how it works. Powered by light and 2 chiral elements, making it moving continuously in one direction. So how fast was this motor? Initially, our motor was rotating once an hour. Now, you cannot build a car with a motor that rotates once an hour. But now we have motors that rotate 10 million rotations per second, and everything in between. Seconds, minutes, milliseconds, whatever. We can design them precisely, because how do we do that? You can change, you know, the sterics, you can change the electronics, etc. Typically, you can modulate all the parameters to tune the kinetics. This is typically what a chemist does. So, then we wanted, and this is more recent work, I want to show you a few examples also of recent things, because people ask me all the time, what are you doing with these motors, you know? So, here, we wanted to make things that couple together, that have more complex functions, you know, couple motions together. And my students, we were discussing this, and we looked at the moon. Now you might ask, are these students in Groningen so romantic that they look at the moon all the time? I don't know what they do in the evening, maybe they do. But There is something special with the moon. You know that, eh? The person on the moon, you see it always from the same face. Eh? We don't see the backside of the moon. But because this is synchronized motion or tidal locking. And we thought, can we build something like that? And here it is. You see, this is the axle, the double bond. It's powered by light. And you see here another axle. And you see now, if you stand here, you see always the same face. It's like the moon going around. This was a delicate design. It took us some work to make it, but this is the first time we could couple motion, yeah? One motion to the other. And it works. And this is our stepping stone to more complex machineries. Synchronized rotary motion. But this is maybe even more rewarding. Now, you know all know what a display is, eh? You have it in your smartphone. These materials are rod-like molecules. Here is a typical example, you know. They are organized like beams in a river. When you put in something gyral, a tiny amount, they form helices, yeah? Helical structures. And this makes a color pixel in your smartphone, in your display. Because if the helix is long, the Bragg reflection of the light gives you red pixel. But if the helix is short, yeah, it condenses, you get a blue pixel. And in your devices, you know, you change the helicity and you get different reflections of light. So we thought, if we take a motor, we change its chirality, you know, when it moves, and we use only 1 weight %, maybe we can expand and contract, expand, contract. And look, within 1 minute, we can make every color pixel. How does it work? Simply because it modifies the packing, the supramolecular organization, and it also amplifies along length scales. But now came the eureka moment of my career. So this is when my students came to me and said, this was on a Tuesday afternoon, I will never forget, 5:15. And they came to me, come to the lab, we want to show you an experiment. They had made a tin film, you see, a tin film of this soft material, the liquid crystal material, yeah? You see here, it is like waves on the sea. Yeah, this is the structure of the soft material. The motor you don't see because it's only 1 nanometer, but they put a glass rod swimming on top, like a boat swimming on the soft material. And then they switched on the lamp. And this is what happens. The whole surface starts to change, you see? The object starts to spin in a clockwise manner. We can spin it clockwise, we can spin it counterclockwise. I don't touch it, eh? It's all autonomous. And you see the color changes, as I promised you. We can continue this rotation now for 48 hours. This is all self-propulsion and amplifying from the level of 1 nanometer all the way to micrometer scale. I tell you, that was a moment in my career when I was there in the lab, I could not speak for 4 minutes. I was completely speechless. But for the first time, I saw with my eyes this object simply because my students switched on the lamp. How beautiful can it be? So what we recently did is we put these motors in liquid crystal polymer materials. So now we can bend. Yeah, you see we can make this kind of bending arm. We have now a piece of plastic, liquid crystal material, that walks over the table when we switch on the light. I don't know if your kitchen, you know, how many plastic bags you have that walk over your table. But we have now a piece of liquid crystal material. When I put it here and I shine with the light, yeah, like this, it will start walking towards the light. We bend a little bit further. You see, we put this in as cross-linkers in polymer materials, and you can see we can make, depending on the chirality, if it's right-handed or left-handed, we can make very complex motions. And I like this one particularly. Look, this phi, yeah? Depending on if we have the chirality correct, yeah, right or left, it can move inside or outside. And this is how we make now all kinds of grippers and soft robotic kind of things, etc. And I will show you a movie how this works. So this is recent results of the past year. So you see, this is the motor. We use it to contract and expand. And then it's part, of course, of this liquid crystal network. So these are robust materials. It's just like a piece of good plastic. And you need only a few of these motors, and it contracts, expands, contracts, expands. And this is just robust. And we can make now a muscle that can pick up something, you know, like this. It picks up some materials. We can actuate. And this is a stepping stone to soft robotics in the future. So, talking about muscles, I want to share with you a few small stories, and then I will finish. But you know, we all know what a muscle is, yeah? But a muscle is not a piece of plastic, yeah? So in your arms, there are millions of these motors that walk, yeah? These walking motors, these biomotors, and they contract and expand, and because these filaments here, these actin filaments and myosin, they glide, yeah? And it was Jean-Pierre Sauvage who made the first artificial supramolecular muscle-type structure. But the most important thing is its amplification of collective motion from nano to macroscopic dimension. You go all the way from nano to macroscopic dimension. That happens in your arm. And when you have millions of them together, yeah, like I showed in the previous example in this movie, yeah, you can actuate, you can make real muscles. But what we did is, what my students did is, they built an amphiphilic motor. So here is a hydrocarbon chain, here is groups, you know, that make it soluble in water, like carboxylic acid groups or sulfate groups. And we can make muscles. They self-assemble. This is supramolecular assembly. They aggregate, and then we add a little bit of calcium, and they form a muscle-type structure. And you can bend this muscle, yeah? It works beautiful, it actuates. But now it's not a polymer anymore. It's just a small molecule that actuates, and we found that you need only 5% of this material. It forms a beautiful bundle. It's 95% water, and then we grow cells in it, because there's a lot of volume to grow cells. And we grow stem cells in it. This is the latest results that my student, you know, I promised the girl to show this picture because she is so proud, my PhD student. She grows stem cells in these muscles, and they can bend, they can actuate, but we can grow muscle cells, we can grow heart cells, and the cells are alive, they grow. And you know, stem cells, I know there are biologists here, cell biologists, stem cells are extremely sensitive to small forces, So they differentiate depending upon the force. So we are now trying to control stem cell growth using this artificial muscle and making these biohybrid systems. Now, finally then, 2D and 3D confinement. Because I always get the question, this is all fine, Dr. Feringa, this is in solution and so, or polymer, but what about surfaces? Because when you talk with somebody from the physics community and they want to make devices, they want to have something on the surface. That's fine. So I'm from the Netherlands. You know, when you come now to the Netherlands, you will still see the tulip fields with the old windmills. These are our modern windmills that you have also here in Hungary, I know. So we built a nano windmill. You see a rotor, axle, a stator, and the legs, yeah? And assemble them on different surfaces, like for instance gold. And it works. So here is what our ancestors built 500 years ago, 20 meters. We built nano windmills, 2 nanometers, 1 billion times smaller. So we have a nano windmill park. It's not powered by wind, by the way, It's powered by light, okay? But they all spin in the same direction. Now, when I talk about this for the first time, I again got the question, your students at the university, why do we pay all this money to you? What are you doing, you know? Playing, you know, building Lego, building nano windmills? I said, no guys, we can make surfaces that are responsive, that move. And in the future, you don't have to wash your car anymore or your windows. Because if you make things responsive, yeah, they can clean themselves. They can heal themselves. So we are working on self-cleaning materials, self-healing materials due to this responsive function. Maybe in the future you will buy a car with a coating that you don't have to wash anymore, or if there is a scratch in your car, you don't have to go to the garage because it repairs itself due to these dynamic functions. Our motors might be too expensive, yeah? Let me make that clear. But once you know the principles, the fundamental principles in the future, together with our technology, the engineers, etc., we will develop that for sure. And yeah, we put them also in crystals. This was another challenge, 3-dimensional. So these are more, I'm sure many of you heard about these metal organic frameworks, these porous materials. They are everywhere now, And so these metal organic frameworks, what we did is we make layers and we make pillars, and the pillars are these motors, and these motors spin. So we can make these porous materials, which are very robust, crystalline materials, but you can make them dynamic, and you can use them for sequestering things from the air purification, or from absorption or delivery. But when you make it responsive to light, you can do a lot of new functions with it. So this is where we stand. We work here together with the Max Planck Institute in Germany and in groups in Italy, etc. but we are very happy with that. And, oh yeah, it was mentioned, a nano car. Yeah, I slipped in these slides, you know, because I thought I should show this. My students were very, very, very jealous of these engineers. Because these engineering students, I don't know about your university, but the engineering students, they go often to Australia, to this solar-powered car race. They go in August or so to Australia for several weeks, and they have this race, 3,000 kilometers through the desert. And they compete with each other. And my students said, can we also go to Australia? And I said, uh-oh, we are not engineers, we are molecular engineers. So then we decided to build a nano car. Here it is, 2 meters, 2 nanometers, 1 billion times smaller. It's a 4-wheel drive, you see? 4 of these motors, they drive it, it's a 4-wheel drive. And it's powered by solar energy or by electricity. And here it is, it moves, you see, a single nano car. It's 4-wheel drive. Yeah, the key question was not, of course, to build a nano car. The key question was, can we get rotation into translation? Yeah, like a real car. That was the fundamental question. And it works, and we could prove it. So we built a nano car. So here it moves. Oh, why doesn't it move? Here it moves, a single nano car. But now the movement, you should realize when you are in the nano world, it's a bit different. Yeah, your muscles, the movement and so, it's a bit different there from the macro world. It's not like a car in the street. So this is likely, we did a modeling, this is likely how it moves, you know. It steps, it walks over the surface. Yeah, this is the nano world. And if you don't believe me, this is now happening in your body. I borrowed this movie from Harvard. You know, this is in your body. You know, if you have the highway from here to Vienna, yeah, or Szeged, the highway is built, and when the car is passed by, they build a new highway, or they break it down. This is all dynamic in your body, these filaments, etc. You see? It builds the filaments in your cells, it breaks it down, and this is how things are transported. It walks over these filaments. So at the moment, we are building highways at the molecular level, and we try to move these things, yeah, very controlled, over these artificial filaments. But that is a big challenge, I tell you, you know, to balance the interaction. So this is, you know, an electric car, yeah, a Tesla, I think. This is our car. Look, this powder. This is 1 billion times 1 billion identical cars. This is typically what a Gammas does. So I would argue our car manufacturing plant is not so bad after all. Eh? By the way, there was also a Formula 1 race for nano cars. Look, Toulouse, 2017. The first ever Formula 1 race for nano cars. Now I come to my end, but not before I ask you the question, will we have nano robots? Yeah? Will nano robots go through your body or do jobs for us, etc.? Some of you might remember this beautiful book and movie, The Fantastic Voyage, yeah? Where a nano robot was in the body and had to go to the brain, you know, to do a repair. So we thought about that, and we built a nano submarine, yeah? Carbon nanotube, 2 enzymes, glucose oxidase and catalase, and then we were discussing about the fuel, not light, but a chemical fuel. And we came to sugar, because there's plenty of sugar in your body. So we propel these things now, yeah, with sugar water, because these 2 enzymes convert sugar and produce oxygen. The bubbles you see here is oxygen. It's like a rocket, you know. It's still extremely primitive, but I don't have to do anything. Just adding sugar water, and it moves. Once again, it's extremely primitive. But what will happen in the future? This is fundamental science. Will we have nanorobots? Is it science or science fiction, ladies and gentlemen? I tell you, in 50 years from now, the surgeon in the hospital will inject a nanorobot that goes to detect a tumor or a defect or deliver a drug at the right spot. But this is all science fiction, and now I cannot resist to use the quote that you mentioned already. I'm a scientist. I'm very bad in prediction, but the best way to predict the future is to invent it. And this is what we all do together, no? Inventing our future. So let me skip this one. Let me go directly to these conclusions. In the art of building small, the perspective, starting with Mother Nature, the cell or the pigeon, We built switches and motors. We built smart drugs, responsive materials. We tried to molecular machines, soft robotics. I think this is all very primitive and early stages. But once you are able to induce motion, it opens up tremendous new opportunities for material science, for engineering, and whatever, etc., also for biomedical application. But of course, I could not have done anything, wasn't it, for all the bright students where I share a passion to invent our future. Sorry, they insisted that I was in the middle. Normally I don't do that. But this is my team of students, you know, and they are my heroes because together we invent our future and make this possible. I cooperate a lot with physics, with engineers, with other disciplines, because biology is the medical people now, but these are the people, you know, that do the work in the laboratory. And yeah, for the young people, they ask me all the time, do you have advice for us? Yes, discover your talent. Follow your dreams, be confident, discover your energy, what is your passion, and very important, discover your limits. How high can you set the bar? Sometimes it's good that you try something tough, difficult, because it gives a lot of energy when you succeed. Don't make it always too easy, you know. But most important, follow your dreams. For all of us, also the senior professors here, it was an adventure to the future. It will be an adventure for the students, yes? Follow your dreams and be confident. That is very important. Now, are there enough questions, ladies and gentlemen? Yes. How to reduce CO2 emission with 95%. How to recycle our materials, I mentioned it before. How to fly without kerosene. How to feed 10 billion people. There are so many questions where chemistry, I'm a chemist, you know, where chemistry plays a central role. Not in isolation, but together with our colleagues in all kinds of disciplines. And then our teaching might also change, eh? We have not time to discuss as much, but you know, virtual reality, interactive learning, artificial intelligence, this will all change also the way we are going to teach and to deal with these complex problems in the future. And also our laboratories will change because we will get automation, robotics, we have to deal with complexity, all this data processing, information, and artificial intelligence. This will be all aspects of the universities of the future. Now, the question, did I know that I would get a Nobel Prize? Chairman, give me a few minutes, yeah? Because I get this question all the time. And I mentioned before, at other occasions, no. Of course, you get sometimes, you get at a conference, they say, oh, this field is very important, you know. At a certain point, people knew that Katalin Karikó would get a Nobel Prize because that made such a big breakthrough, you know. The fundamental research, you know, in the 80s, all the way to make these vaccines, etc. But once again, if you want to go to the Olympics this summer in Paris and you want to win a medal, don't dream about this medal all the time because you never win a medal. You work, you get up early in the morning, train damned hard, and maybe when you are lucky, you know, you win a medal. I was working with my students in the lab to follow our passion, to develop science, to do discoveries. But then I was called by a colleague from the University of Illinois on a Wednesday evening late, and he said, Ben, you were on American television last night. And I said, come on, you're kidding. Why should a Dutch scientist from the University of Groningen in the north of Holland be on American? Yeah, you were last night on television in The Simpsons, you see. And this was the week before the announcement of the Nobel Prize, 2011. And The Simpsons predicted we would get the Nobel Prize in chemistry. Richard Saar, Mörner, Feringa, Sonek, and Schirra. Mörner got the Nobel Prize in 2014. I had to wait another 2 years. And let me tell you, you know, the next morning when I came to the lab, my students had seen this on Twitter, of course, and they came to me, you will get the Nobel Prize. Predicted by The Simpsons. I said, look guys, I'm a scientist. If you are on primetime American television, predicted to get a Nobel Prize in the program of The Simpsons, this is about the highest honor you can get in your career. So I don't need to go. It took a little bit of time before I had the privilege to go to Stockholm. Here's the king and the queen, the princess and I got this. It's like a fairy tale. Like, you know, Sissy, eh? It's like a Sissy movie. This is the banquet. 1,200 guests, you know. I was sitting here somewhere next to the princess. It was absolutely flabbergasting. You never forget, this is a once in a life, it's a dream, you know, etc. And then, after the Nobel Prize, they said to me, what are you going to do now? You stop with science? No, I said, science is my passion, you know, and I have the research team and I want to continue, of course. But I want to continue, I teach, I do chemistry, you know, I do science. But I also want to go to the public and to go to schools. So I started this foundation. We go to elementary schools and to high schools. And so when I came back in Groningen, they had invited 800 kids from school. Elementary school in the morning, high school in the afternoon. And I talked, I discussed, I gave lectures, etc. And then they said, oh, now we want to give you something. Yeah, as a thanks for that you spend all this time with the school kids. But yeah, he has already a gold medal, so we cannot give him that anymore. So then they looked at America. You know, America is big and Holland is small. So what is the situation? Sir Fraser Stoddart, which was a co-laureate in Northwestern University in Chicago, he has 2 parking spots. You see, reserved parking for Sir Fraser Stoddart, 2016 Nobel Laureate in Chemistry, permits F01, F02. This is a limousine, just in front of the chemistry department. But then they said, we have another problem because Ben always never comes by car, he always comes by bike. So now you know how we do this in Holland. In the biking shed, you see, there is this plaque, this size. Yeah? I have my own biking spot. You see, bicycle parking space reserved for Nobel Laureate. I'm extremely proud that I have, maybe I'm the only Nobel Laureate in the world that has his own biking space, you know. So this is the honor I got in Holland. And let me finish, yeah, because I've been talking already a bit long maybe, with my hero, Leonardo da Vinci. When nature finishes producing its own species, man begins with the help of nature to create an infinity of species. And for all the young stars here in the audience, the students, imagine the unimaginable. The future is yours. Much success. Thank you so much.
That was really outstanding. I mean,
thank you.
We expected something good, but this is really top. So,
my pleasure.
Are you brave enough to take?
Oh, sure.
Who would like to start? Sure, on the left.
Yes, please.
Thank you very much for a very nice talk. And I have a question about discovery.
About?
Discovery.
Yeah.
Discover. Yes. So, did you discover molecular motor, molecular switch, etc., or did you try to make this interesting molecule by making a plan, or did you expect this?
Yeah, we wanted to make a system that could move in a unidirectional sense. Yes, so to go from left to right, yeah, and not in both ways. So the directionality was crucial. So we designed it that it was powered by light, yeah, and it was the chirality make it, yeah, in one direction. But when we had made it, yeah, you saw these switches, eh? And we saw, one of my students, we made one, and then we saw that it was doing this motion, and then we discovered that it was not switching back, but it was switching forward. And then we realized this is 180 degrees in one direction. If you do that twice, you have 360 degrees. Yeah? So you also have to, when you can design beautiful things, and you can do experiments, but also be aware if something is not exactly as you have predicted, yeah, a little bit different, unexpected things might help you a lot, yeah? Because then when we realize that, yeah, it worked beautiful, yeah? And then we could make it continuously moving, etc. Yeah. So yeah, it was by design, but also it was a little bit luck that it flipped over, you know? Eh? Because if it had partly flipped back or so, we would have a problem, because then we still had to re-engineer it. Yeah. Okay?
Thank you very much.
Thanks.
More questions?
Yes, please. Yeah.
Once again, thank you for the great talk. My question is whether you have ever faced a synthetic problem in which you had to use the motor ability of your molecules. So, for example, you wanted to make a reaction come true, but first you had to switch the orientation of the motor, and then you could do the synthesis then.
Oh, yeah, this is connecting it to synthesis or catalysis.
Yes.
This is a fantastic question. I had no time because I had already a lot to show you here. But what we did is, we took this motor and we put organocatalytic functions. You know, organocatalysis is an important area. I know they work also in this university on this. And so what we did is, you know, you go, maybe I should show the picture. Wait a moment. Let me go back to these 4 steps. Oops, where is my motor? Here. You see, what we did is, we put these organic groups here and here, yeah? And you realize, when you rotate, yeah, the groups can come close together or farther apart. So in catalysis, organocatalysis, often you need 2 groups that work together, cooperative function. Yeah, and so what we did is we rotated and the groups came together or the groups went apart. When the groups are apart, it's a lousy catalyst, but when they come together, it was a very good catalyst because of cooperativity. Simultaneously, we can change the chirality. So we have a catalyst now, one catalyst, yeah, that makes a racemic compound, it makes one enantiomer, and it makes the other enantiomer. And all with the same catalyst, just using light to control the state of the catalyst. And we can make that also in a defined sequence. First racemate, then R, then S. Or first racemate, then S, then R. So indeed, you can make a responsive catalyst. Yeah, unfortunately, I didn't discuss this, but we have several examples where we can tune the catalytic function, taking advantage of these motors as a kind of multi-step switch. Yeah, where we model each other. And this is what we use also for other applications where you want to control different functions. My dream, of course, is at a certain point to use these machines to make step synthesis. Step 1, step 2, step 3, step 4. These kind of things. Real synthesis machines. And with these solid materials, I showed one slide, you remember, on the porous materials, crystalline morphs. We try to make real molecular factories. Don't ask me now, my students are working on this, but maybe in 5 years from now I can give a lecture about that. I don't know, it's tough, it's a tough problem. But yeah, catalysis is something beautiful, of course. We did it also the other way around. I showed you this propulsion with enzymes, with sugar, but we also make synthetic catalysts that can make rotary motion. But the motor is not so good. It rotates, but after 48 hours it was going all kinds of side reactions. It was not so stable. So we have to redesign and make a better one. But light has a big advantage. Light is beautiful. You can tune the energy, the wavelength. It's non-invasive, you know. Yeah? I irradiate here, there it happens, you know, on the floor, or there it happens. Yeah? So it has a lot of opportunities compared to chemical-driven systems. Although in your body, except for your eye, all the other systems are powered by enzymes, chemical-driven. But there's still a lot to be learned. Yeah. But thanks for the question, you know. This was really exciting to make multi-stage catalysts, you know, and control the chirality in this way.
One more? Don't be shy.
Yeah, this is the opportunity, you know. I'm here. Tomorrow I'm gone. If you want to ask me about anything. Okay, don't be shy. Oh, there is a question by the lady. Sorry? No, better take the microphone. Then the others can also hear.
Thank you for the inspiring lecture. I just wanted to know if when you design or think about designing a molecule, do you take into account any theory, any computations for that?
Computations?
Yeah.
Is that, yeah. The
Yes.
question was if you do computational studies. Yes. we do now, before we have made several motors, you know, with different speeds, with different properties. But we do calculations quite a lot. So my students do basic, we are not theoretical chemists, but I cooperate with theoretical chemists who do the real advanced calculations, yes? But the basic calculations we do ourselves. So like structure, because these molecules, you can do structural calculations, you can calculate energy barriers, and you can calculate absorption spectra. And so that is what we usually do before we design new motors, because it might be take 2 months before we synthesize a motor. My students say, oh, let's first calculate if the speed will be something, yeah? If the speed will be in the order of minutes or it will be days or whatever, because it makes a difference for the application. So we do this kind of calculation, yes. And the prediction is pretty good. I'm quite impressed how these methodologies work these days, you know. So I'm not an expert in calculation, but some of my students are really good in that. They got training in that in the groups that are experts. And recently, but you can calculate a lot, but to calculate excited state energy profiles is still very difficult, pathways, you know. So we recently discovered, more or less by accident, now we do the calculations to explain, but we did the accidental discovery that when we put an aldehyde group in such a motor, that we boost, this paper came out 2 weeks ago in Nature Chemistry, when we boost the performance dramatically. So we have now motor that has a quantum yield, you know, efficiency of more than 80%, which is better than in your eye. So we are really excited about that, and now together with our colleagues in physics to do the femtosecond laser spectroscopy and the theoretical people, we try to explain why this is possible, because it might guide us to the next generation motors. So thanks a lot for the question, because it's very important. You can design all kinds of things, but at a certain point you also want to understand, just like a car manufacturer, you want to know how to design the next generation car, you know? And if you have some rules and some insights, it will be very helpful. Yeah. So, yeah, very good. Thank you.
Thank you.
Okay, Gabor. Where's the mic?
Thank you. It's just a very quick question. Can you use polarized light to activate only a certain subset of the motors depending on orientation?
Yeah, this is a really a very intriguing question. You know, we put the chirality in the motor, yeah? Okay, to control the directionality. But now to put the chirality in the light. And we did that with our switches, not with the motors, because we did it originally with the switches. So we had to push it out of equilibrium, either to the left or to the right. And I work on asymmetric catalysis, as you know. I have some catalysis team. And when you work in asymmetric catalysis, people that work in this field, they know you need 90% selectivity. Otherwise, you cannot publish these days, you know, because this field is advanced. And the enantiomer selectivity, was 0.07%. 0.07%. It works. Yes, you can get a bias with circular polarized light, but the efficiency less than 0.1%. My students were not very excited. We still could publish the principle, in a very nice journal called Science, but we said, okay, we proved the principle, but this is not the way to go forward if you want to make a muscle or you want to move things or you want to make a smart drug or whatever. But for some basic fundamental physics, it's really important, because what we do now I give another story, sorry guys, I give another talk, but we put these motors in liquid crystals or in other materials that are luminescent. And due to the change in chirality, we can generate right circular polarized light or left circular polarized light with very good intensity and very good selectivity. So there, people get really excited about it, because in device physics, when you make luminescent materials, the polarization of light is really important for the efficiency and the outcome. So we have now a system where we can change the polarization direction quite efficient. And we work together with the people in the material science in Eindhoven, Philips and so, to work on these luminescent systems. It gives a lot of opportunities. So that is thinking the other way around. Not using circular polarized light, but making circular polarized light. And that works really beautiful.
And the very last one.
Okay.
Thank you, and thank you for the nice and very inspiring lecture. And probably it's going to be a very good closure as well, how you respond to my question, because you showed us a journey which was kind of like a success story, and you inspired the young people and probably all of us to dare to dream.
To dream, yeah.
And dream big. But I'm sure you had some experience in your life, in your research life, where your bold ideas were not very well accepted by the community, to say it politely.
I tell you two stories then, two small stories if I'm allowed. First of all, I also was a PhD student. And I worked for this American professor, and he gave me a tough problem, and I knew my colleagues in the lab said this will never work. Okay. At the end, I got it working a little bit at the end of my PhD. But I was working for 6 months on a project, one of these sub-projects, and it was terrible. Nothing worked, and I worked harder and harder, spent more hours in the lab, even going in the weekend. And I will never forget, I went back to the village because I was playing soccer still in the local team. And I went back on a Friday night, and I came home and on the farm, and my mother said, "You look terrible. Do you eat properly?" I was simply, working too hard, and I was so frustrated, So then I took the message of my mother. Maybe you should relax a little bit. She had no idea what chemistry was, of course, and what the research was. And so what we did is, after the 6 months, I went with some friends. One of the guys had a car. We went to Germany for a week. And we had a good beer, yeah? We enjoyed, relaxed, my head was empty. And I went back in the lab. I took a bit of a different approach. And within 6 weeks, I had the material for a Journal American Chemical Society paper. Suddenly it worked. So sometimes it's good to go to the pub or go to a concert or a movie or spend an evening with your friends, This is my advice. Work hard, but also sometimes you need a little break to clear your mind. Yeah? And the second, don't give up too easy. I worked on catalysis, and we worked on organolithium compounds, We work on green yards and those things to make carbon-carbon bonds. And lithium reagents, every chemist knows they are so reactive. To make a carbon-carbon bond, one enantiomer catalytically with a lithium reagent, it looked almost impossible. So we worked on that for 20 years. That is to say, we tried many things, and I tried to convince a student. Every next PhD student that worked in my team, I asked him, can you do some of these reactions? Several of them refused. They simply had heard already from their friends, this never works. So they give me another topic. Then after 20 years, believe it or not, I had a Spanish postdoc that was not so influenced by my students. And he was working in this area of this asymmetric catalysis. And on Thursday night, he went apparently with his friends to the pub, because on Friday morning he did this experiment at 9 o'clock, and he took the wrong bottle of solvent. When he told me, he came to my lab in the afternoon, to my office in the afternoon, he said, it worked, 90% yield. I said, this is impossible. Yeah, he said, I looked this bottle by accident. I said, you use this bottle, this looks dangerous, with lithium reagents. I was a bit scared. But then we repeated several times in the lab, and we got it work fantastic. And then we suddenly realized what we had done wrong for 20 years, because nobody used this kind of solvents. But it has all to do with the aggregation of lithium reagents, with the catalysis, we understand the mechanism. So we got, believe it or not, butyl lithium, you all know what butyl lithium is. It's dangerous and it's very reactive. CC bond formation with 99% enantiomer selectivity. Thanks to this mistake of this guy, sometimes you need luck, you need perseverance, and you also, sometimes it's good that you make a bit, don't blow up the lab, but you are allowed to make maybe a mistake, and sometimes you discover something, because we all think, oh, it's this way, and it might be a little bit different. So this was a lesson for me, that once again, after 20 years, we succeeded, and we turned failures into a great success. And so, we can learn a lot from Mother Nature and from our experiments and whatever. And once again, of course, you have to know when to stop, but also don't give up too easy, because there might be gold waiting for you, just there, not here. Thank you so much for the question.
I said the final, but there is one person.
Oh.
Like to satisfy.
Oh.
Please wait for the microphone.
Oh, sorry. Maybe you can use a micro because otherwise the people in the back will not hear it.
What about the lifetime of the nanomachines?
Yeah.
Macroscopic machine works well at the beginning and slowly went wrong. But this one, if you apply individual molecule for a job, it will be work well and immediately stops.
No, the lifetime, you have to be realistic. When you have organic materials, and you do reactions, chemical reactions, or you do photochemistry or whatever, of course there is this issue also of that they might degrade or fatigue or whatever. So we have motors that are very stable, that you can move for days. But we have also systems that get, after an hour, they get destroyed because of side reactions and so. But usually we know exactly how to make them stable and to continue motion for many days, no problem. But honestly, when you make organic materials, you all know that they might photodegradation or other deterioration might take place. I always take the example of your smartphone. That is organic materials. And they work beautiful for years with electricity and light, no problem. In your body, I didn't realize that until I discussed this with a cell biologist. Your body, there are so many things that go wrong all the time. You cannot believe that I stand here. I was learned, maybe I'm incorrect, you can correct me. 40% of the energy in your body goes constantly in repairing your body. Can you imagine? 40% goes into repair mechanisms because molecules degrade. Molecules, proteins are hydrolyzed. All these things happen. Even DNA. How many repairs are there in DNA cell? That's a lot. So it's amazing that it works, And so we have to learn also, and also plastic and all these materials at a certain point, they have stabilizers there to prevent them from radical degradation, because if you put a piece of plastic outside in the bright sun and it has no stabilizer, it will degrade, after some time. And this happens with many materials. So this is all a balance between stability, fatigue, degradation, all these things, So you cannot claim that a material will exist forever. That's nonsense. Except for your cathedral and the buildings that were built 500 years ago. They stand. This is amazing. How our ancestors managed to do that, These robust buildings.
So thank you again.
Thank you.
Don't be afraid. You can ask questions because he's not going to leave us.
No, I will be here.
We're going to try to relax. So anyway, because you appreciate the personalized parking place for a bicycle.
Yeah, I do.
Then this looks like very sort of official, but it's not.
Oh.
If you open it, it's not exploding. It's not chemistry anymore. This is a very personal thing, which just has happened in this time. And this side is, of course, your lecture announcement. But the back side is your quote and a few signatures of the audience.
Oh, fantastic.
So I think this is very unique from this sense.
Yeah, this is great.
Anyway, congratulations.
Thank you so much. Thank you.
Thank you.